This could be you or me, as in the last 5 major earthquakes, over 2 lakh Indians died without even knowing what wrong they did. Thankfully, we survived. And we should stop and think what we can do to protect ourselves and generations to come from the wrath of earthquakes. India, like several other countries of the world, is prone to earthquakes. On the basis of earthquake risk, India is divided into 4 major seismic zones. The red zone is the most vulnerable to major quake activity, and the green area comes a close second. We construct houses and other buildings to live, work, and to protect ourselves against the natural calamities. But do we truly bother to ensure a long-lasting and safe building? Many of those who died could have been with us if they knew how structural engineers and architects use some of the fundamental principles of physics and mathematics to create buildings which can absorb, disperse, and withstand strong seismic forces. Those of us who had incorporated these features in their building structure survived with least to nil damage. As the structural scientists say, earthquakes don't kill, unsafe buildings do. In India, over 85% of the population lives in masonry buildings. The Disaster Management Division of Ministry of Home Affairs, Government of India, referred a project related to the testing of masonry buildings to the Department of Earthquake Engineering, Indian Institute of Technology, Roorkee. The idea is to formulate and effectively demonstrate the efficacy of seismic strengthening of the popular 3 types of masonry buildings: brick, block, and stone masonry. The experiments are to be conducted on the railway wagon shock table testing facility available at the department.
The shock table comprises of a 36-meter long railway track having mild gradient on either side. The rails are marked at half-meter intervals as a guide for positioning the wagons before releasing to achieve the desired impact. Shock table forms a rigid steel platform which is used as the base for dynamic testing of building masonry models. 10 helical steel springs have been mounted on both ends of the table to convert the impact into earthquake-like wave. Loaded wagons are placed on the track inclines on both sides of the shock table. The weight of each wagon is adjustable. The wagon on the left side is allowed to roll down the incline to collide with the shock table platform. Due to the impact, the shock table wagon starts to move and collide with the other stationary wagon on the right side and receives impact in the reverse direction. In this way, the model constructed on the shock table receives 2 shocks simulating earthquake-like motion. The intensity of the shock is controlled by positioning the loaded wagon at different distances on the track incline before release for rolling down.
2 half-scale, single-room brick masonry models are constructed simultaneously on the shock table. The first model is constructed using popular construction techniques as we have been doing for years. This model has been constructed without any earthquake-resistant features. In the second model, all seismic strengthening arrangements specified in earthquake safety codes like vertical reinforcing bars at the corners, jam steel around the openings, and seismic band at lintel level are incorporated. As per chosen scale, half-size bricks are laid in 1:6 cement sand mortar, providing space for the vertical steel bars at the corners and near the openings. The gap around the vertical bars is filled in 1:2:4 concrete mix with 6 mm size aggregates after every 5 courses of the wall construction so as to develop full bonding. The walls are completed up to the lintel level and a monolithic horizontal seismic band is provided on all 4 walls so as to integrate the perpendicular walls. In the actual construction, vertical reinforcement is embedded in the plinth masonry into the foundation and is passed through the lintel band and anchored into the roof slab to develop its tensile strength. The reinforced concrete band has the same width as the thickness of wall. The vertical thickness is kept to the half scale. Then the wall is completed up to the roof level and the roof slab is laid as was done for the traditional model. The two models look exactly the same. The traditional model is constructed using conventional techniques, while the earthquake-resistant model incorporates corner vertical steel bars, jam steel bars around the openings, and horizontal seismic band on all the 4 walls at the lintel level, which will be safe if an earthquake occurs. We shall see by impacting the shock table. Before testing, the table and models are instrumented using acceleration meter to measure the intensity of the simulated earthquake and the effect on the models. In the first shock, the loading wagon hits the shock table from the left side, simulating a low intensity shaking. With each subsequent shock, there is a gradual increase in the intensity of the shocks. So, what do we see? Even after the 4th shock simulating an earthquake of severe intensity, no damage is seen in the masonry model with earthquake-resistant features. But the conventional model is badly damaged. The 5th shock is made even stronger. The model with earthquake-resisting elements still remains undamaged.
This is the wall in the same line as the direction of the shock. So, this has the behavior of out of plane bending. Now, as we go, we see here how this wall tends to fall out, and then when we come to this wall, which shows different behavior than this particular wall, because this is now in the position of a shear wall, and a shear wall has a behavior of the shear failure, as we can see here. It is a diagonal tension failure. So, we see here that this unreinforced model constructed in the traditional manner is failing. On the other hand, this is a model of the same type with the same geometrical details, same dimensions, same wall thickness, same roof thickness. So, everything mortar etc., everything is the same, but the difference is now it has vertical reinforcing bars at the corners, all the 4 corners. It has also vertical bars at the jambs of openings, as we can see here, window jambs and the door jambs, and also it has a seismic belt or band actually, which is going inside all round the building. Now, these reinforcing details are keeping the whole building intact and in very much integrated behavior of all the walls put together. So, you can see the difference.
Earthquake strengthening of buildings could have saved thousands of lives in Bhuj, Latur and Kashmir earthquakes. At places where it is difficult to get bricks, people use concrete blocks for constructing buildings. Therefore, the second set of tests is conducted using concrete block masonry construction. Solid concrete blocks of half size have been used to construct two half-scale similar models on the shock table. Both the models are constructed in the same way as the brick models were constructed. For construction of the wall with corner steel and jam steel near the door and window openings in the earthquake-resistant model, special blocks with semicircular holes are used. The two models differ from each other as the strengthened model additionally has corner vertical steel bars, jamb vertical steel bars around the openings, and horizontal seismic band on all the four walls at the lintel level. During the testing of the models, shock table is imparted shocks of gradually increasing intensity. In the shock equivalent to a moderate intensity quake, cracks started to form diagonally at the corners of the window openings in the traditional model and gradually spreading towards the corner of the wall. Horizontal cracks are also visible just above the lintel beam, extending to the end of the wall and reaching up to the corners. There is a slipping of the wall from the foundation. These are typical shear cracks observed in masonry buildings after a moderate size earthquake has struck the region. However, the earthquake resistant model remains undamaged even after this shock. For the next shock, the loading wagon is placed further up on the incline to simulate an earthquake of severe intensity, which could occur in higher earthquake zones 4 or 5 in the green or red areas as per the seismic zoning map of India. The traditional model further loses its strength and stiffness. The next shock is of slightly higher intensity as compared to the previous shock. Here too, the earthquake-resistant concrete block masonry model shows no sign of distress. There is no damage and the model is intact even after imparting a severe intensity shock to it. In the next and final shock, the intensity of shock loading is further increased so as to check on the strength of the earthquake-resistant model under a much more intense shock. The performance of the earthquake-resistant concrete block masonry model is indeed being put to the ultimate test under this shock loading. Traditional model could not withstand the severe intensity shock. However, there are no cracks in the earthquake-resistant model. The earthquake-resistant features have improved the building under earthquake shaking. India is a collage with myriad cultural and religious colors. The diversity in India is even spread across its geographical terrain. As a result, at different places, people construct buildings using different materials available locally. Like in the hilly areas, one would see that a majority of buildings are made using stone masonry construction. The loss of lives in earthquakes of Uttarkashi, Chamoli and Bhuj underscored the necessity of earthquake strengthening of the stone masonry buildings. half-scale single-room models are constructed on the shock table. As before, the first model is constructed using traditional construction techniques used by common man. While constructing the earthquake-resistant model, features like the corner steel and the jam steel around the openings are placed so as to develop tensile strength. For providing vertical bars in the stone masonry, casing pipes with a diameter of 50 millimeters are placed around the steel bars and the masonry is then built. After construction of 3 courses of masonry, the casing pipes are raised and the cavities are filled with concrete mix and compacted. In the construction of walls, through stone or header is placed at regular intervals. In each layer at the corner, a long stone is put into the alternate layers of walls, strengthening the building structure. A horizontal seismic band is provided on all 4 walls at the lintel level. In the stone buildings, another horizontal seismic band of the same dimension as of the lintel band is provided on all 4 walls at the eaves level, and gable band is extended up from this band. In the earthquake-resistant masonry model, wooden trusses and cross bracings are used instead of the usual rafter system in the roof. In order to prevent sliding of the roof tiles, they are bound with wire mesh at the ridge and the edges, and concreting is done on this mesh. The 2 masonry models differ as the strengthened model has wooden trusses and cross bracings, header or through stones, cornerstones, corner vertical steel bars, jam vertical steel bars around the openings, horizontal seismic band on all the 4 walls at the lintel level, horizontal roof band on all the 4 walls at the eaves level, and gable band at the 2 ends reaching up to the tiles or gable walls. The models are subjected to shock loading, each with increasing intensity. This shock is similar to an earthquake of a severe intensity, likely to occur in Zone 4 areas in the seismic zoning map of India. This resulted in cracks opening up in the traditional model, whereas the model with earthquake-resistant features showed no distress, a visible proof of the strengthening of the building structure. For the final shock, we take the loading wagon further up on the incline and release. The resulting shock simulates a very severe earthquake likely to occur in Zone 5 on the Indian seismic zoning map and affecting cities like Bhuj and Chamoli.
First, the corner has opened out, and then the diagonal cracks had appeared, and this is the beginning of the collapse of the building. If we provide the seismic belt like this throughout the building and which holds all the walls together, then the cracks will not develop, and then it will not initiate the triggering of the collapse of the building, and it will be safe.
Yes, indeed. But how much extra does it cost to build an earthquake-resistant house? Well, it will cost just an additional 5 to 6% of the cost of a traditional building and ensure complete safety for the family. A safe dwelling unit is equally necessary and important for those of us who have already constructed a house and cannot afford to rebuild due to financial and other limitations. Hence, there is a need for external strengthening of the already existing buildings. This is known as retrofitting of the existing structures. Traditional model is prepared for incorporating earthquake-resistant features post-construction. For putting the header or through stone, few stones at regular intervals are taken out from the walls. These holes are then filled with an S-shaped iron rod, an M15 grade concrete mix. For corner steel, wire mesh is nailed and plastered. Similarly, other earthquake-resistant features like jam steel, lintel band, roof band and gable band are incorporated externally. For preventing sliding of roof tiles, they are secured by wire mesh and concrete, as was done while constructing earthquake-resistant model. Now, on the shock table, we have two similar models. These two have the necessary strengthening features retrofitted in one while built-in the other. For the first shock, the loading wagon is released to generate a low-intensity earthquake. With each subsequent shock, there is a gradual increase in the intensity of the shock loading. It is clearly visible that both the models are showing the desired results. Even after a severe intensity of simulated earthquake loading, there is absolutely no damage in either of the models. Constructing a new building with seismic resistance increases the cost by 5 to 6%, while retrofitting an old house will cost 10 to 12% of the reconstruction expense. But incorporating earthquake strengthening features makes a huge difference, the difference between life and death. These tests prove beyond doubt that earthquakes don't kill, and the structures with safe design and construction will neither collapse under the impact of an earthquake nor kill the inhabitants. Buildings constructed with proper care and incorporating earthquake-resistant features have successfully withstood the wrath of earthquake even at places like Bhuj. You can safeguard generations to come by building structures which have earthquake-resistant features like the vertical jam steel around the door as well as the window openings, vertical steel at all the corners, horizontal seismic band on all the four walls at the lintel level. In the stone masonry structure, additional roof and gable bands. These features, at a very little additional cost, would make the difference between life and death, not only for you, but also for your loved ones. Remember always, earthquakes don't kill.